Okay, this is the first PowerPoint information on Unit 3, Chemical Reactions. And we're going to talk about the math part of this unit, which is stoichiometry. All right, first of all, let's just talk about chemical reactions basically. Chemical reaction is a chemical change that occurs when substances become new substances. You could be asked from a reaction or some information, what is evidence that there was a chemical change taking place? So here are the four major areas: production of heat or light, formation of a gas, formation of a precipitate, and then a color change. So if we talk about, we can kind of go back and review. Remember, physical changes are just a change in properties, but it's really still the same substance. Phase changes are a great example of that. I just wanted to point out that we can represent both physical and chemical changes with a balanced equation. So if you notice, the water evaporating or vaporizing is the first example, and then the chemical reaction of hydrogen gas and oxygen gas that would require electric current would produce water. So that is a chemical reaction, since we have water forming from completely different elements. But no matter what type of situation we have to obey the law of conservation of mass, and both sides have to be balanced. In this example, if you look at the PowerPoint, this is actually like a movie, and you can see the water molecules moving. So the question is this physical or chemical? Well, if you see the water like organized here, and then if you look at the video, you can see that some of the water molecules will change to a separated particle, which is supposed to represent a gas. So that would have to be physical, because as we learned in Unit 3, only the hydrogen bonding between the water molecules is being broken so that water can change to a different phase. So let's talk about stoichiometry. So the basis for stoichiometry, and the reason these math relationships work, is because we can have a balanced equation and we can get mole ratios, so that we're able to start with one piece of information about one substance in a reaction and be able to convert to something completely different based on this ratio. So like here we have a 1 to 2 to 1 to 2 relationship, and depending on what we start with, if you notice, this is a limiting reactant problem because we're starting with a mass of hydrogen, and this is a mass of oxygen. But no matter what we're starting with and what we're trying to figure out, the whole basis of this is no matter what we start with, and again, I'll circle these again, 4 grams or 16 grams, once we get these into moles, is the mole ratio that would be able to determine which of these reactants is limiting. So like the actual reaction for this math problem is that water example, the elements forming water. So if I write this, and again, I need to make sure it's balanced, you can see where these mole ratios I've circled are coming from. It's from the coefficients that give a relationship of all these substances to each other. So what the thing about AP Chemistry that makes it a little bit more challenging than the first year class is that we learn different topics in individual chapters, and so now what we need to do is we need to think a little bit more globally, because we've got to be able to think, okay, what have I been given in the problem and how can I change it to moles? So I've tried to think of many different types of information that we could be given, and then the relationship we need to use to be able to calculate moles, because again, it's when we have moles that we can use the balance reaction and the mole ratio to get information about another substance in the reaction. So let's just go through a lot of these different examples. So if you're given mass of a solid, we can look at the periodic table and calculate the molar mass, and then divide and get the moles of that substance. Then we could do a mole ratio. If we have a solution, you're probably going to have the volume and the molarity given, so we can use that relationship and multiply and end up with moles. Now, if we're given a gas, there's a couple different options. Most commonly on the AP exam, we'll be given a pressure, a volume, and a temperature, and we can use the ideal gas law, which is on our formula sheet, and solve for N, because we know N is moles. So, and again, we'd have to, use the correct R based on our pressure units, but that's another way we can solve for moles of a gas. Then we could do a mole ratio to find out information about a product. The other thing that's a little bit less common but still important is STP, standard temperature and pressure, is on our formula sheet. And, standard temperature is 273 Kelvin, standard pressure is 1 atmosphere, or any amount that equals 1 atmosphere. If we're told we have STP conditions and we're given like a volume of a gas, we can use this molar volume relationship where we would actually, if we're given volume, we'd have to flip this over, divide by 22.4, and then we can end up with moles of that gas. And then the last example is if we were given atoms or molecules. Avogadro's number is also on the formula sheet. It's on the front page in the first section. We could use that to change a number of molecules or atoms to moles. So once we have those moles, this is when our balanced reaction becomes critically important. We need to use our mole ratio as our second math step, and then some other, we might have to repeat one of these calculations I mentioned, or use a different one and convert moles to whatever they're asking about, grams, liters, molecules, using one of these methods above. All right, the next section of math problems is going to be calculating percent yield. It would be nice if all of our reactions had 100% yield, but the chance of that happening are extremely small. Sometimes there are impurities in a sample. Sometimes samples go through other reactions that we don't expect. If we're doing a precipitation reaction, maybe some of the precipitate is stuck on the filter paper and we just can't, recover all of it to get the highest percent yield possible. So percent yield can never be over 100% and should really, I don't know a case I've ever had a situation where it actually was 100%. The higher the percent, the better, but 100% is not very likely. So I love this analogy. In my house, when we make cookies, the cookie dough is eaten along the way, so we always get less cookies than expected. So that is a great way to remember what's going on here. Our actual yield is the cookies we actually bake, and that's the product we collect in the lab. And our theoretical yield is, what the recipe says we should end up with, but of course we eat the cookie dough, so we don't. This is going to be the answer to our math problem. So this formula is not on the formula sheet. It's very simple to remember. Percent yield, it's actual over theoretical, A over T, times 100 to get our percent. And remember that the actual yield always has to be smaller than the theoretical yield, or we would get over 100%. So here's a great example. This time we're given a balanced chemical reaction, which is great. We have 45 grams of NO. We have excess sodium hydroxide. It's not limiting reactant, which is nice. We don't even have to worry about that. And then it says 6 grams of water were obtained from the reaction. So what you're supposed to realize is that this 6 grams is actual. Does it tell you its actual yield? It doesn't. The product information given when it's asking you a percent yield question is given to you if they don't come right out and say it's actual. So that has to be actual. What are we supposed to do? We're supposed to start from the amount of the reactant and convert it all the way to whatever units these are of that product. So we need a theoretical amount for this water that should have been produced. So how do we do this kind of problem? Well, anytime we start with grams, we know we got to change it to moles. Then we've got a mole ratio, and then our final step, we don't want moles of water because we've got to compare it to whatever units are given for the actual yield. We've got to convert that to grams. So let's look at that math. So here is my molar mass. I'm dividing by Here's my 1 to 4 mole ratio, molar mass of water. There's my theoretical yield. Notice it has to be higher than actual. I divide times 100 and there is my percent. Many stoichiometry problems that are AP questions actually come directly from lab data, because hopefully you'll get to do some kind of lab, or I know you might have done a couple of labs last year that pertain to this same information. So the fancy word for the first lab is called gravimetric analysis. If you think about the root of that, it looks like gravity. We're really not we say the word weighing, we're actually taking masses of substances. So basically, we're taking the mass of something in a reaction, and so we can calculate something else. Okay, so gravimetric analysis is about massing. A lot of times it's about a precipitate. Collecting a gas over water. So this is a reaction that's going to produce a gaseous product. We want to collect the gaseous product, not let it go into the air, actually make it go into some kind of graduated container, maybe an inverted graduated cylinder or gas collecting tube, something so that we can measure the volume of that gas we're collecting from that reaction. And then the last one, redox titration, we'll talk about with oxidation reduction reaction. So here's kind of an overview of gravimetric analysis. So again, this is used a lot with precipitation, because when we mix two solutions together, we can end up with an insoluble compound. And how can we recover that? Well, we can filter it out. Okay, so here is, a little diagram of what this would look like. We've got our funnel, filter paper. We're pouring the products of this, we've mixed together these two solutions. We have a solution that has this solid. We want to keep rinsing the beaker until we get all the solid to go through the filter paper. So the filter paper and the funnel will collect the solid. The liquid that goes through is called the filtrate. And what we can do is, so here we go, we've collected the solid. The key here is, this is wet. And a lot of times you'll rinse it with water so that all the dissolved ions end up in the filtrate. But the key here is this has to dry. You could, speed it up with like a lab oven. You might leave it on the counter overnight and let it dry on its own through evaporation. But the drying, filtering it and then drying it is a key. Once it is dry, it's going to be masked. Okay? Once we know this would be like our actual yield, then we can calculate something of the reactant, like how much of the reactant maybe did this product come from. So that's one lab that's very common. And then the collecting the gas over water. Notice, and I've written the reaction out, we've got potassium chlorate, it's being heated. It's obviously, there's going to be a solid product, KCl, that's going to stay in the test tube, but it's this oxygen gas that normally would just leave the test tube, but see, with this stopper and tubing, we're forcing it into this container that was previously completely filled with water. So what happens is, as the oxygen gas bubbles go through the tubing, it goes into this inverted jar, it bubbles up, displaces the water, and normally, this in this example you don't see it, but this would be graduated so we'd actually know the exact volume of the gas that was produced. So here's the reaction. If we have this mass of potassium chlorate decomposes, what volume of O2 would we collect? So maybe this is a good example. They're asking to predict that. They're telling you a pressure and, interestingly, vapor pressure of water. So hopefully this rings a bell from a previous unit. So if we look through the rest of this, what do we need to do? Well, see, this beginning information is for a solid. So I can change grams to moles. But see, this is what I want to know about. I want to know moles of the gas. So what I'm going to have to do is change grams to moles, but see, that's not enough. That just gives me moles of a solid. This is asking me about a gas. So that's why I need my mole ratio. I've got 3/2. Here are the moles of oxygen gas. Hopefully these pressures ring a bell. You know, any above the surface of any liquid is its own gas. That's why we have the water vapor pressure. This is that specialized version of Dalton's law. It's a very simple calculation for number 2. You just have to remember to subtract out water's vapor pressure from the atmospheric pressure. The remaining number is the pressure that the oxygen gas is exerting. So once I know moles of the oxygen gas, I've got the pressure, the temperature is given. I just need to have Kelvin. Here we go with moles of a gas. Very common to have to solve PV equals nRT in a free response question. So notice this was in torr, and since one of the R gas constants on the sheet also has a torr version, there's no need to change this to atmospheres. You could, it's just extra work, takes more time. Plug in all your numbers, divide the pressure to the other side, and we end up with this many liters. If you felt like changing it to milliliters, you could. Notice that wasn't asked. It just said what volume. This is not necessary. If you made a mistake in converting liters to milliliters, you would not get credit. So I would highly recommend, unless it asks for a specific unit, leave it as that final unit.